Okay, we're only going to spend one day on chapter 5. And that's because it's not something I'm going to ask you on a test, but this class is ultimately called Probability and Statistics. And I'd like you to have a really good understanding of why that's important, because as I mentioned before, it's kind of the backbone of this class, because what we're really trying to do is predict things. We're trying to figure out what we think is going to happen in a situation ahead of time. That's what you do statistics for. And it's amazing some of the predictions that you can actually make. And some of that is, well, probably the best example we have so far is the empirical rule, in the sense that we are predicting, as long as the distribution is normal, bell-shaped distribution, that we kind of already know that predictably 68% of people are going to fall inside 1 standard deviation of the mean. And so again, that allows us to predict the future with things like, as I said, buying clothes or shoes or something, buying the right percentage of them. In other words, if people's shoe size was an average of an 8 and the standard deviation was 1, we'd want to order 68% of the shoe sizes between 1 and 1 standard deviation of the mean. And then 95% of the shoe sizes within 2 standard deviations of the mean. That's predictive. That's the idea. So we're trying to do the best we can to kind of guess the future. And so I want to talk about probability a little bit today. And it's actually really simple, really simple. Well, as long as it's, let's try this. I've got a picture of this in a minute. I'll probably pull this up, but let's just say you have a bag of M&Ms and you pull it out and you count them all up, and there's like, let's say this is what ends up happening. There's like 6 oranges. This is just a playful example. Nobody cares about M&Ms in terms of probability. Let's say 8 of them are red. 9 of them are green. 4 of them are blue. There's other colors, brown and stuff, but let's just keep it simple. So, language of probability. So what's the probability of you reaching into the bag then, since that's the count? What's the probability of you reaching into the bag and actually getting an orange M&M? Well, probability is simple. It's just sort of, I like to think of it like this: ways to win divided by ways to play. Your book explains this in a much more complicated way. It uses the language of the probability of an event. I'm using winning just because that's something that people kind of relate to when they're playing a game. But does it make sense if I say ways to win? I said, oh, what's the probability of getting an orange? Well, you have 6 oranges. So that's how many ways there are to win. That's how many oranges you have to choose from. But then how many M&Ms are there total? Well, if I add all of these up, what is that? 14, 23, 27, is that right? 27? Does it make sense? That'd be the probability of drawing an orange then? It's not hard. Or of course, if I said, okay, fine, what's the probability of drawing a green? You'd say, okay, well, there's more of those. There's 9 of those, but still out of 27. Does it make sense that you have all kinds of ways you can write that? In other words, you could write it as 6/27. You should feel good about the fact that if somebody wanted you to reduce that, like maybe your My Open Math assignment will ask you to reduce from occasionally, fine, I can reduce 6/27. I could certainly just divide it. If I take 6 divided by 27, I get 0.222. So there's a lot of ways that you can write that. Probably this is the best, only because you could think of this as a percent. Notice that'd be 22.2%. Or maybe 9 out of 27, 9 divided by 27 is 0.33333. So as long as the game, if you will, is pretty simple, then not bad at all. Probability is not complicated. It gets complicated if you start playing like a card game or something and you're going to draw 5 cards and you ask what's the probability of getting a pair. It starts to get hard to count sometimes, but backbone of this, not complicated at all. So let's see, I'm going to hand you something right now. So does it make sense that just like those 2 examples I gave, those probabilities are always going to be, I mean, you can think of it as a percent. Does it make sense it's always going to be less than 1? Like that came out 0.22 and 0.3. That has to come out less than 1 because there can't be more ways to win than there are ways to play. So I'm going to highlight a couple of things on the sheet that I just gave you in a second, but let me write the rest of them here. And there's a couple of other interesting things. So what's the probability of red? You'd say that's 8 out of 27. I'm just going to write this as a decimal this time. 0.297. And finally, the probability of blue, which is 4 out of 27. 4 divided by 27 is 0.148. Approximately every one of these I had to round off. So notice all less than 1. So probabilities are always going to be less than 1. The probability of something happening can't be more than 100%. Now, if I ask kind of a dumb question and said, what's the probability that I'll draw an M&M? Then that would be 100% because that's the only thing that's in the bag. So technically it could be equal to 1, but basically without, a weird circumstance, every probability is going to be something less than 1. Notice your note sheet that I just gave you points that out. The probability, so P for probability, the probability of some event is going to be less than 1 and bigger than 0. Does it make sense? You can't have a negative probability. So you're always going to have a smaller number divided by a bigger number, 7 divided by 12, 8 divided by 19, something like that. Therefore, you're always going to get answers to probability questions that are somewhere between 0 and 1. So what do you notice about the rest of this? You have a calculator. What happens if you take these probabilities right here and add them all up? Now I rounded them all off, but what happens if you add up these probabilities right here? Let's see, I got 0.22, 0.222 plus 0.333 plus 0.297 plus 8. When I added all those up, did you not get 1? Now that's not a surprise because that basically means that's the only things that can happen. I mean, if that's all that's in there, orange, green, red, blue, that's all the M&Ms that are in there, then one of those things has to happen. So if I add up all this probabilities, I get it 1 or 100%. We got kind of lucky to get exactly 1 there since I rounded things off. I don't know if that makes sense. If you did it over here, maybe it'd be a little bit easier to see. You know how to add fractions, I hope, because these have a common denominator. If I added all of those up, I'd be adding up the numerators. The denominator stays the same. I end up with 27 over 27 because that's all the possibilities there are. And so that's the second thing on this note sheet that's kind of important to point out. Does this speak to you from your previous knowledge of what that summation symbol means? So if I add up all of the probabilities, then I'm going to get 1 or 100%. That's going to happen every time. So this isn't super important. It's just expect that when you're doing kind of a probability problem. Numbers less than 1. Okay, so let's play with something a little bit more interesting now. Whoops. So let's consider the illustration of dice. If I'm rolling 2 dice, I'm going to roll 2 dice. If I asked you, what's the probability that I'll get a sum equal to 8? This isn't so easy. Now, there's a lot of games based on this, and you can appreciate, for the sake of something like a casino, they're giving out prizes and so forth, some kind of a prize for, winning at that game. Craps is based on that. And in order to give out the correct prize, they got to own this. Like, you got to understand this really well. So if you roll 2 dice, what's the probability that the sum will be 8? This is kind of a much harder question, as it turns out. But I want to illustrate, it's no different than what I said before. Ways to win divided by ways to play. You just have to count them up. But given that we rolled 2 dice, that's much harder than just kind of drawing one M&M. A second ago, we drew 1 M&M, and I asked what's the probability it's orange, and it was 6 out of 27. But what if we drew 2 M&Ms out of there, and I said, what's the probability there that you'll get a green and a red or something like that? That starts to get more complicated, and I'm going to show you a way to kind of survive counting that in just a little bit. But let's start with dice. So what's the probability that a sum is an 8? Well, you should say, well, I can get one by rolling a 6 and a 2. That's a way to get an 8, right? But the interesting thing is, that's not the only way. You could also roll a 4 and a 4. You could roll a 5 and a 3. I guess that's it. And I don't know if you know this, but it's complicated by the fact that if your first dice is a 6 and your second dice is a 2, like I wrote there, that's actually not the same roll as if the first one is a 2 and the second one is a 6. So even though you kind of throw them out on the table and they just kind of land there, and you say, you think of yourself as getting a 2 and a 6, and you don't really think about which one is which, does it make sense that one dice could be a 6 and the other could be a 2, or switching it? That's actually a separate count. So notice there's only one way to get 2 4s, but a 5 and a 3 and a 3 and a 5. So there's actually 5 different rolls then. So ways to win, there's actually 5 different rolls that you could get that would get you an 8. But how many total rolls are there? What do you think? Why? Because you're actually right.
It's just the number of.
Yeah, that's right. There's actually 6 numbers on each dice. And so any of the first dice could be any of 6 numbers. And then the second dice could be any of 6 numbers. And what you just did was something called the multiplication rule. In other words, if there's 6 choices for the first one and then 6 for the second, so I could count them. I could say 1, 2, 3, 4, 5, 6 for that first dice. And when the first one is a 1, does it make sense the second dice could be anything 1 through 6? So there's 6 possibilities. When the first dice is a 2, the second one also could be anything 1 through 6. So there's another 6, and so on and so forth for every one of these. So that's why there ends up being 36 possibilities there. So as a shortcut, if there's 6 choices for the first and 6 for the second, I get to multiply those. So the probability is 5 out of 36 that you'd roll an 8. So that's not very good odds, right? If I divide 5 by 36, that's only 0.139. Again, I think it's kind of nice to write these as decimals, even if you have to round them off, because then they look like percentages, and it's a little easier to see that 13.9% is, oh yeah, that's kind of small. That's not that likely to happen. Excuse me. Now, what's the probability of rolling like a 2 then? A sum of 2. Well, still out of 36. What rolls will get you a 2 though? Yeah, only a 1 and a 1. Like that's the only way. So if you don't think about a game like this, you might think, oh yeah, all those rolls are the same probability. But there's actually only one way to get a 2, and that's to get a 1 and a 1. And there's only one way to get a 1 and a 1. So therefore, the probability of rolling a 2 is only 1 out of 36. It's even less. And so they're not all the same. Again, this isn't necessarily obvious. Let's look at a little simulation of this. Excuse me. Let's see here. So this is interesting, kind of a side note, but you can do some amazing things with Excel. This is a simulation that I made as a part of another class where we spend actually more time with this for simulating rolling dice. So if I roll the dice, notice that's kind of fun. You can I actually made it so that it appears that you just rolled a 5 and a 6. Notice it marked it over here as, oh yeah, you just got a sum of an 11. Again, maybe you see, hey, that's not very likely, because to get an 11, you can get a 5 and a 6 or a 6 and a 5. So there's actually 2 ways, 2 out of 36. That's a pretty small possibility. So if I roll it again, oh, look, I got the same roll again. Well, except for, I think the first time it was a 5 and a 6, and this time it was a 6 and a 5. That feels kind of unlikely that would happen, right? That you'd get an 11 twice in a row. But that's kind of the point of probability, is that's not super likely to happen, but it will happen sometimes. Next roll, got something different. Got a 7, 6 and a 1. And then a 5 and a 3. So there's the 8 that we talked about earlier. So now I'm just going to roll quite a few times here. So this is kind of cool because I can roll the dice like 50 times without having to chase them across the room and write it all down and all that kind of stuff. So this is kind of a simulation. Notice 7 appears to be the most likely thing to happen. I want you to think about why that would be. What rolls get you a 7? Notice a 2 and a 12 don't appear to happen very often. Again, that should make sense, because the only way you get a 12 is with a 6 and a 6. That's one roll. Just like a 2, you can only get it with a 1 and a 1. So do you see that the distribution here is kind of symmetrical? And this is just one experiment. Let's see, I'm going to roll 360 times here quickly. So notice there's a theoretical frequency over here. And so this is what you would expect to happen. If you roll the dice 360 times, you would expect 10 times you're going to get a 2, 20 times you're going to get a 3, 30 times you're going to get a 4, and so on and so forth. This is what you'd expect. Notice, though, when you experimentally do this, is that exactly what's going to happen? No, but it's close. So we expected 10, we got 12. We expected 20, we got 22. We expected 30, we got 32. Notice the 5s is a rather surprising one. We thought we would get 40 of them, but we only got 27. So that particular experiment, that kind of lagged, the 5s kind of lagged behind. That's the idea behind probability. Just because you kind of know what should happen, that doesn't necessarily mean that would happen. That's what's going to happen on a given day. So why is 7 the most frequent? Why is it predictably? It was predictably the highest number by theory, and then also that's also what came out over here. It was also the highest one over here. Notice it was pretty close to what it should be. It's supposed to be 60, and we got 59 of them. That's because, let's see, how many choices, what's the count of how many ways to get a 7? I can roll a 6 and a 1, a 1 and a 6, a 5 and a 2, and a 2 and a 5, and a 3 and a 4, and a 4 and a 3. So there's actually 6 ways. 6 out of 36. Now, do that on your calculator. Take 6 out of 36. What decimal does that give you? Yeah, it should be 0.16, like 16%. And just so you understand how I got this, since that's the percentage, that's what you'd expect, that's the percent chance of getting a 7. Now, since we rolled 360 times, this is just like the test question I went over a second ago. Leave that number in your calculator and say times 360, since that's how many times we rolled. How many times would you expect then to get a 7? If you take 0.1666 or whatever it is times 360, sure enough, you get 60. So that's how I did this. In other words, that's where that experiment came from. So probability is kind of cool. If dice kind of fall into the category of math in the sense that we know how they work, there's 6 equal choices on a dice, but there are other things that are kind of less simple in the real world. It isn't always math that allows you to determine it. For instance, if you were thinking, I want to, sell some product, and so what colors should I make? By the way, this is what the M&M company did. They actually make a certain percentage of each color. It's not just even. And they did that entirely based on market analysis, like what people's favorite colors are. The idea was just that they would hope to sell as many M&Ms as possible, which it seems kind of weird because you probably don't care when you buy them. You just eat them because they're good and taste like chocolate. But notice there's no mathematical reason as to why, like what number of M&Ms would be a certain color. That's entirely just somebody having to run an experiment to check. Whereas dice, entirely mathematical. So that's interesting because it's entirely countable. Let's see. Let me show you something kind of playful, just for the fun of it. How many people in a room this size, what do you think the chances are 2 people would have the same birthday? It's a pretty small class. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's only 10 of us counting me today. What do you think the chances are that 2 people have the same birthday? Watch this simulation. I wonder if this will surprise you. Notice you can actually simulate people's birthdays by choosing a random number between 1 and 365, because that would kind of place them at one particular day in the year. So what I did with this simulation is I just did that, let's see, 23 times. So this is like 23 people in a classroom. And so if I ask the question, what's the chances that 2 people in a room of 23 people have the same birthday? Your gut reaction to that would probably be, that's not really very likely. because there's 365 days in a year, and so 2023 is not that many people. So watch this. I'm going to click this, and that's going to represent kind of choosing a random room of 23 people. Notice when I did that, there were actually not just two people with the same birthday, there were actually two different people with the same birthday. Does that surprise you with only 23 people in the room? So here's another day. Notice, oh, yep, there's two people with the same birthday in that room too. Think of it as just like walking from room to room to room. Do it again. Nobody that time. Went into that room, there was nobody with the same birthday. Next room, oh, yep, there's two people with the same birthday. Next room, yep, two people with the same birthday. Does that kind of surprise you? That there'd be that much overlap? That many people with the same birthday? Again, this is just playful. Nobody cares about something like this, but it's the idea. Probability is sometimes kind of a challenge to count. All right, I want to show you kind of a foolproof way to count it and a couple of principles behind it. One more simulation. Okay, so this is kind of like a marble game. And there's a bag of marbles, and inside it are 5 red, 4 purple, and 3 green. So if we only draw 1 marble out of that, you should feel pretty good about what the probability of drawing a particular color would be. But what I want to show you this time is, what if there was more? What if you're going to draw more than 1? And we asked for all the different probabilities from that. So notice the possibilities here. So I hope you would say, yeah, if we're just going to draw 1 marble, and I said, what's the probability of it being red? You would say, oh, well, there's 5 reds divided by 12 marbles. So 5 out of 12 would be your chance of drawing a red marble. Yeah, that's what probability is. But if we pick 2, does it make sense? We have a lot more, it's a more interesting game now, in the sense that, well, you could get, well, look at the choices. I wrote them here. You could have a red and a red, or a red and a purple, or a red and a green, or both purple, or a purple and a green, or both green. Like, that's the 6 possibilities that you could get. So what I want to play with is like, well, what's the chances of those happening? Okay. Red. So I'll come back to that in just a second. Keep in mind, these are just playful, stupid examples. Nobody cares about marbles. Like, you're not taking this class so you can go play marbles with kids. The larger goal, and that's what we're going to jump into in the next section, the larger goal is to try to predict how people are going to behave based on running simple simulations. What do we say there was? 5, can't see it now. Can't look at both screens at the same time. Was it 5 red? I think it was 5 red. Oh, we're going to look at this. I guess I don't have a choice. I'm going to have to go find it. Five red, 4 purple, 3 green. Okay. So we're going to draw two of these things and look at all the possible outcomes that we could get. So very hard to count with once you're making the game a little bit more complicated. So watch this. Let's see, let's go here. So let's say this is red, this is purple, and this is green. So would you agree? We said this already, but if you just make one draw, then we said 5 are red out of the 12 that exist. So this is 5 out of 12. That's your chances of drawing a red marble. And since purple, there's 4, then that'd be 4 out of 12. Notice I could reduce 4 out of 12 to 1 out of 3. That'd be fine. And then green, there's only 3. So that'd be 3 out of 12. So that's your chance of drawing just one marble. Notice, what do you notice about those probabilities? Every one of them is less than 1. And if you add them all up, you get 1. Those are the 2 facts that are on your note sheet that I handed you. Those probabilities are less than 1. And because that's all the marbles there are in the bag, if I add those probabilities together, I get 100%, I get 1. But now let's keep drawing. Let's draw a second marble out of this. So let's see, I got to do this carefully here. So would you agree, if I go down this arm right here, then my first draw was a red? And would you still agree that I could also draw a second red marble? So that would represent red, red right there. But my question to you is, what's the probability, I want you to think about this, what's the probability that your second marble is red, given that there were 5 reds in the bag and you drew one already that was red? What's the probability that your second draw is a red? What you think about that? Yeah, you don't have 12 marbles anymore. Does that make sense? And you don't have 5 red marbles anymore either, because you already drew one of them. You agree with that? So that's exactly right. That's 4 out of 11. So your chances of your second marble being red would be 4 out of 11. Now your second marble doesn't have to be red. It could be purple. What's that probability? What's the probability of drawing a purple? Yeah, notice you still have all 4 purple marbles. You haven't drawn any of them yet, so you still have all 4 of them. But again, you only have 11 marbles left because you already drew one red one to even get to this point on the chart. And it could be green. And there are 3 green marbles out of the 11 marbles that are left in the bag. Again, notice those probabilities right there. 4 out of 11 plus 4 out of 11 plus 3 out of 11. That's 11 out of 11. That's still 1. So let's keep going. So this could be red, this could be purple, this could be green, and the same would be true for this last one. So again, this going down this branch, your first pick was purple. So you have to think about that. What does that make these probabilities then, given that your first choice was purple, since you already made that choice? Just want to give you a second to think about it. So So yeah, because we went down, it's kind of like branches of a tree. So if my first pick is red, then this is my other possibilities. This is the probability for my second choice. But if my first pick happened to be purple, then does it make sense I still have all 5 reds? So this probability here is still 5 because I still have 5 reds to choose from. But I still only have 11 marbles because I already chose one of them right here. So that's why I only have 11 marbles left. And I only had 4 purple marbles total. So since I already drew one of them right here, does it make sense I only have 3 of them left? But I've never chosen a green yet, so I still have all 3 of my greens. Notice still 5 out of 11 plus 3 out of 11 plus 3 out of 11 is still 11 out of 11. So really complicated, like if you play cards, for instance, and you're maybe you play blackjack or something like that, and you're thinking, oh man, should I take another card and try to get 21? That can be really complicated. And a tree diagram actually you can actually draw out every single possibility with every probability on the way and still actually figure it out. But it's so much more complicated if you're just drawing 2 marbles instead of 1. Lastly, what if your first choice over here was a green? So I went down this branch. So my first pick was a green. Just like before, all of these, then I still have 11 marbles to choose from because I already chose one of them. But again, how many choices are red? Well, you haven't chosen any reds yet, so you still have all 5 red marbles to choose from. You haven't chosen a purple either, so you have all 4 purple marbles to choose from, but you did choose a green. So that means you only have 2 left that are green to choose from. As before, 5 11ths plus 4 11ths plus 2 11ths is still 11 out of 11. So the key though is how do you work yourself down the table? So would you agree that if I was to put this into words, you really went to get down this one, you chose a red and the key word is and then you chose purple. So this represents a red and a purple right here. And to work down that, basically, and I'll write this over here, there's a shortcut to this. And that's that you get to multiply those. You get to multiply those probabilities together. So for instance, in this arm, if I take 5 out of 12 times 4 out of 11, what is that? 20 out of whatever 11 times 12 is, 132. That's your probability right there for getting a red and a red. In the same way, we can do this with every single one of these. So this would be a red and a purple. And since I multiply 5 times 4 is 20 again, notice it's the exact same probability. That's interesting. 20 out of 132. But for a red and then a green, that'd be 5/12 times 3/11. That'd be 15. So this would be a red and then a green. Notice that's less likely. Maybe it makes sense to you why that should be less likely because red has 5 and green has 3. So that's not as likely. Anytime you include green, there's only 3 green marbles. So getting that's going to be kind of a less likely outcome. Notice the order of that though. This is a red first, like you chose a red first and then you chose a green later. So let's keep going. So for this next one, if I take 4 out of 12 times 5 out of 11, that'd also be 20. So this would be purple and then red. This is the first time that we've seen this, but do you agree that these two right here are kind of the same exact kind of outcome? In other words, if you reached into the bag and just grabbed 2 marbles, notice this first example is first red and then purple, and the second one is purple and then a red. That actually is different, just like the dice. A 2 and a 5 is not the same as a 5 and a 2. No, it looks the same when it lays on the table. But in terms of counting probability, if you don't recognize that those are 2 different rolls, then you're not going to be able to predict this. So let's see, I'm gonna keep going and write all these down. Notice this last one is a purple and a purple. That'd be 4/12 times 3/11. That'd be 12 out of 132. This is a purple and a green. That'd be 4 times 3 as well. That's also 12 out of 132. This would be a green and then a red. 15 out of 132. This is a green and then a purple. That's 12 out of 132. And then the least likely, a green and then a green, because that's the least number of marbles. 3 out of 12 times 2 out of 11, that's only 6 out of 132. So that's the least likely occurrence. So we won't take the time to do it, but sure enough, if you add all of these probabilities together, every single one of these, you're going to get 1 again. Every single probability that you look at down here is all less than 1. But does it make sense? Armed with this tree diagram, you could invent all kinds of, if you will, kind of casino games. Like if I said, what's the probability of you drawing 2 marbles out of the bag and they match each other? Let's see, what does it mean to match? That means, well, like this, red, red's a match, purple, purple's a match, green, green's a match. So there's actually 3 ways to win here. There's red, red, which is 20 out of 132, or you could also get purple, purple, which is 12 out of 132, or you could get green, green, which is 6 out of 132. So there's actually 2. You don't have to be this good at this, so don't worry about this too much, because we're not going to solve problems like this. I'll show you what you need to know later on. But in this direction, moving down the table, this is kind of an and statement. In other words, what happened here? We got a purple and then we got another purple. So in that situation, you multiply your way down the chart. But anytime you use the word or, in other words, hey, how many ways could I match? Well, I could get a red and a red, or a purple and a purple, or a green and a green. In that case, I actually get to add those probabilities together. So thanks to this table, you can actually literally see every possibility in front of you. Therefore, you'd be able to kind of count them all up. So let's see, if I add that up, that'd be 32, 38. So that's the probability that you'd match. Doesn't matter which color. Again, as I said, you could certainly divide that, turn it into a decimal if you wanted. 38 divided by 132. So that's like 0.288. So that's like a 28.8% chance that that would happen. So it's a lot more complicated if you start choosing 2 cards, those kinds of things. I don't know what different games you've played and so forth, but if I just draw, well, let me ask you this question. If you know enough about cards to answer this question, what's the probability that you would draw a face card if you just drew one card out of the deck, what's the probability that it would be a face card? There's 52 choices because there's 52 cards in the deck. And if you know cards, there's jacks, queens, kings in 4 different suits. So jack, queen, king, spades, jack, queen, king, clubs, hearts, diamonds. Yeah, so there's actually 12. So there's 12 face cards out of 52 cards. So it'd be 12 out of 52. That's not so bad because that's only just drawing one card out. But if you start saying, okay, well, let's play a game that's more interesting than that. Let's draw 2 cards out. Or as you may know, there's lots of card games where you draw 5 cards. And so it gets really complicated to be able to kind of count this stuff up. The amazing thing about kind of drawing a tree diagram is you're literally drawing every possibility. And as long as you kind of understand that you work your way down the table by multiplying as each time that you jump down the table, down the tree. And then you add as you work your way across. What's the probability of getting, say, a red and a green? And I'm not going to write this out, but when I say that, I'm thinking of drawing 2 marbles simultaneously. Therefore, I'm thinking of this as like a red and a green is the same exact thing as a green and a red. I'm counting that as the same. I don't care what the order is. Most games, when you play them, you don't really care what order the cards were dealt in. So does it make sense? Just like the previous example, I'd say, oh, look, a red and a green is 15 out of 132. But then there's also this other way, getting a green and then a red. That's also 15 out of 132. So that'd be 30 out of 132. Notice that's less likely to happen than matching. 30 divided by 132.227. So armed with this tree, you could make up all kinds of games with this. If you think of this as being some kind of a casino game, you could make up all kinds of ways for people to win. They could win. You could say, what's the probability? Actually, I'll ask you this now. What's the probability that you draw 2 marbles, but let's say none of them are green? No greens. Can you figure that out based on what I have written up there? Well, let's see, which ones of these, how many possibilities are up here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Of those 9 possibilities, how many of those don't have any greens? All we gotta do is add those up. And there's not very many greens, so that feels pretty likely. So let's see. That one doesn't have a green, 20 out of 132. This one doesn't have a green, that's 20 out of 132. This one does not. This one does not. This one does. This one has a green. Every one of these has a green, so I guess that's it. It's those 4. Do you agree with that? So that's 60 and 12, 72. Notice that's pretty likely. 72 divided by 132, that's 0.545. Notice that's over 50%. So you can ask kind of all kinds of interesting questions about this. Okay, so let's watch the simulation of this. Let's see, I'm going to turn off the graph. So notice your first pick here is purple and green, and that showed up over here. So again, this is how bar graphs are made. Notice right now there's only one chosen, but notice it says one up there. So you've basically got one purple and green. So then I pick it again. Notice same thing happened again. You got another purple and a green. See how it says 2 up there now? So that happened twice in a row. Now, we don't know, did we get a purple and a green or a green and a purple? Well, we do up here. Purple was the first one and the green was the second one. This time we got a red and then a green. Notice that's labeled over there. And then a red and a purple, that's labeled. So now I'm just going to pick a bunch of these. So we're playing the game over and over. Notice it tells you how many times we played there. Since we were a second ago dividing by 132 every time, did you notice it was always over 132? I'm going to go until we've played 132 times. So do you see the distribution of actually what took place? Again, experimentally, if you play this game and you played it 132 times, every time you play it, it's going to be a little different. You understand that? That's the important part of probability. On a given day, a casino might lose money on a particular day, and then obviously they would hope that the next day they kind of make that money back. Overall, they're going to make money because they understand probability well enough so that in the law of large numbers, it's ultimately going to go in their favor. But on a given day, you actually might win, which is why people play, because it's kind of fun. So notice the difference between theoretically what should happen. You should get 20 red reds, and sure enough, in the experiment, we got exactly 20 red reds. You should theoretically get 40 red purples, and our experiment was 39. Do you see how closely that the math, if you will, was kind of modeled what actually took place in this experiment? That's kind of the beauty of the way probability works. And so as far as what we need to understand it for in this class, can you appreciate that if you're trying to predict people's behavior, who are people going to vote for, what kind of clothes are they going to buy, what kind of classes are they going to sign up for, those kinds of things, the ability to kind of predict what's going to happen. And maybe you can appreciate something more financial, like in the stock market, you're trying to predict whether stocks and stuff are going to go up and down, or what's going to happen on a given night in a football game. Maybe you watched a little football this weekend. They set up a whole bunch of betting around who's going to win and by how many points and so forth. And if you understand the probability of those things, then you're able to kind of predict what's going to happen in the future. That's kind of the power of what statistics is about. So can you see that what we did here by drawing that tree diagram, and I showed you that quickly. I don't expect you to be able to understand that super deeply. I'm not going to ask you on a test to draw a tree diagram and so forth and figure out probabilities. But isn't it cool that our experiment here matched the reality thanks to the tree diagram so accurately? Notice in this case, the one that was the most off is purple green. It was only off by 2. But the important thing is, watch this. If I start over and I do this again, am I going to get exactly the same result the second time I do this? Think of this as like day 2. Day one at the casino, it operated pretty accurately, pretty closely to what we would have thought. But tomorrow's another day. So we get up the second day. I'm going to play the game another 132 times because that doesn't take too long. How about this time? Did it perform accurately this time? Notice green was quite a ways off. There should have only been 6 times that we got green, and yet we got 11. So if you're paying a prize out for that on that particular day, there more people won that prize. Maybe they lost a little bit of money there. Notice it's still close. 12 and 13 is really close. Notice this one's way off. We would have thought we would get 30 red greens, and we only got 23 of them. So it wasn't, this is not the same. Do you see what I'm saying? Like, probability wise, on a given day, it's not necessarily going to match this perfectly, but over time, it's going to match this really well. It's kind of the idea. Each given day is going to be a kind of a different experiment. So the idea behind probability is just trying to nail down what percent chance something is going to happen so that then you can kind of predict accordingly. So my job as math department chair is to try to, put the number of classes out there that students are going to sign up for. And it's been ridiculously crazy in the last, 2 years just because of COVID and so forth. And, do people want classes online? Do they want them face to face? And so, I have to just make a guess. But the problem is my guesses cost a lot of people a lot of problems, because if people don't sign up, then I have to cancel the class. And maybe it did work for 5 people, but now I got to cancel the class. And you've probably had that happen to you. It's compliments to you for, being able to stick with your education during this crazy time. But that comes at a cost. If I could predict that really well, that would be really great, because it's hard on the teachers when I tell them, okay, I'm sorry, I'm gonna have to cancel your class because there's only 5 students in it. It's hard on students. It'd be awesome if I could actually predict what people were going to do so that I could, put the right classes out there to kind of match what people really wanted in terms of Zoom offerings and web offerings and face-to-face offerings like this. But it's hard to predict because real life is not like, marbles in a bag. I can't know what percent of, I don't have any great way to know what percent of people want things. Does it make sense? My only way of knowing that would be to, do an experiment or, call people and say, what would you prefer? Do you want Zoom classes or do you want live classes? And I could gather an experimental percentage by just asking people their opinion on something. Real life is not like marbles where you can just predict exactly what you think is going to happen. You actually have to go run a sample. You have to take a sample of people's opinions. And then I could maybe make an intelligent decision. I mean, that's the idea behind statistics. Okay. Let's see, is there anything else I want to say about that? No, I don't think so. Okay. So we haven't talked about this. Let's kind of switch gears now. You owe me, I'm going to pull this up. You should be working on hand-in homework number 2 right now. So you're in the middle of working on this, and this is, from the last test, actually. I hope you've pulled this up and already started working on it. I just want to use the last 30 minutes or so to kind of elaborate on how to find equations for lines. We've played with this stuff a little bit, but I just want to do one more section of it. So to that end, I'm going to give you okay, so you're looking at something that looks like this. And notice there's a best fit line on it. And again, this relates to the concept of probability once again, because I won't take the time to make up make up real data for this. Notice there's 4 data points on there that are graphed, and I've drawn a best fit line through those. And so the idea then is to predict the future. I mean, if this is global warming or something like that, I'm trying to predict, what I think would happen down the road. That was the last question on the test, was talking about the length of a crocodile, and you were finding a best fit line and trying to predict down the road, how long is this alligator going to be at a certain age and so forth. That's exactly what we're talking about here, is kind of making an educated guess. Now you can see that this particular data, it's like started low and then it went high and then it was a little low and it went high. It's kind of jumping around a little bit. But if we're trying to predict the future, that line is the best that we can hope for. So again, this is very much related to probability. So I will post this after class. You can make some notes on yours too. But we've agreed that this is the x-axis and this is the y-axis. We've talked about the fact that slope can be found by counting the rise over the run, or by just doing the math, y minus y over x minus x. We've talked about that. So I just want to do one example where we kind of cheat and use the calculator to do it, and then where we kind of do it ourselves by hand. So let's try to find the equation of that red line, that pattern for this data. Let's try to find it ourselves by hand. So let's see. What I want you to find is a couple. Notice it doesn't go through any of the green points. So I got to find other points that I think it goes through. Let's see. This one looks pretty good. It's not perfect. Do you agree it's not perfect? If I look really close, does it exactly go through that point? No, not exactly, but it's pretty close. Let's see. And is there another point that goes through? Ooh, look, this one looks really good right here. That one looks fantastic, like it goes perfectly through it. So I'll pick those two. So the slope of the line. Well, in this case, notice each box, this isn't as complicated as some of the problems. Each box is actually just worth 1 here. So I could actually just count the rise over the run really easily. So I'm going to do this both ways. Well, from here, 1, 2, 3, 4, 5. That's a rise of 5. It's up 5. So it's up 5 and then right 1, 2, 3, 4. So it's a rise of 5 over a run of 4. So that's the slope of that line. Easy to count. Or what's the coordinates of that point? Well, let's see. This is 7, 11. Isn't this 7, 11? That's the point 7, 11. And this point over here is 11, 16. So there's the 2 points that I see it going through. Does it make sense? I could go 16 minus 11 over 11 minus 7. And I also would have got 5 over 4. I mean, that's, excuse me, that's why that formula works. To get the rise, you can just do it mathematically by recognizing, hey, this y value is at 11. And if this y value is at 16, then how far is it going to be if I go from one to the next? Does it make sense that you'd be subtracting 16 minus 11 to get that distance of 5 right there? So do you understand that I now know this equation is y equals 5/4 x plus something? So that's where the slope goes. I know my line looks like this. I know the equation of my line looks like that, y equals 5/4 x plus something. We've been saying that this is where it crosses the y-axis. Notice I can look at this and see that it crosses, well, notice it's pretty close to 2, but it's a hair above it. If I was to guess, I'd probably say 2.1 or something like that. But this is kind of cool because you don't have to guess. Does it make sense that these 2 points right here have to work in the equation? That's what it means for this line to work. Those points have to work in the equation. In other words, and I'm just going to pick 7 and 11. If I put 7 in here, then 11 would have to go in here. Like that has to work in that equation. So let's see, that would be 5/4 times 7. Oops, that's not a 7. So there's only one unknown in that, and so I can solve. Now the graph told me it was around 2. Let's see if that actually happens. Again, I'm hoping that you have some basic math skills. If I multiply 5/4 times 7/1, I multiply fractions straight across, so that's 35/4. No reason I can't do this with decimals. What is 35 divided by 4? That's 8.75. So to figure out what B is, if I subtract 8.75 from both sides, I get 2.25 equals B. Notice that kind of fits the graph. It was indeed a hair over 2. I just took one of the points, any one of them. I just picked that one at random. No, it doesn't. Actually, we'll redo it with the other one. So the end result then is, now that I know what B is, I would say the equation is y equals 5/4 x plus 2.25. But yeah, how did I know to pick 7 and 11? Well, I didn't. The other one should have worked as well. The other one was 16 and 11 for x and 16 for y. So if I put 11 in for x and 16 in for y, because it's supposed to go through that one too. Let's see what happens this way. 16 equals 11 times 5/4 would be 55/4. 55 divided by 4 is 13.75. If I subtract 13.75 from both sides, hey, look at that, I get the same answer. 2.25 equals B. So no matter which 2 points I chose, I got the same exact answer. So again, the powerful side of this is I now think I have a model. I have a model for this data, which again, if this is the length of an alligator or something of that nature, I'm just trying to predict how a stock is going to grow. I'm trying to predict how enrollment's going to be at a community college, number of cases of people that have COVID, those kinds of things. I'm trying to predict that. I now have this equation, the power of which I can now plug numbers in and use the equation for something. So you do this, you're better at this. You're not as good at finding the equation by hand. I think that's just kind of cool to be able to do. But remember, that's actually the hard way. That's kind of a pain in the neck. Like we only do this by hand just if somebody asks us, and I am asking you to do that on your hand and homework. But go ahead. Yeah.
I just have a question about the graph.
Yeah.
So the points on it, it goes to like 240, 600.
Right.
There's only 5 lines in between. It's really hard to figure out like where exactly it's actually what.
And
You understand what I mean?
I think so.
It's like in the middle of the line, like each line doesn't do something. It's like we got like 35 or 40. Is it 40? Yeah. But it's not exactly 40.
Well, let me finish this and then we'll talk about that. So notice I had no choice here but to kind of do my best to pick a couple of points that I thought my line went through. And so this is decent, but that was a lot of work. Way better, if you're allowed to, is to use all 4 points and use regression. So notice these points are exact. This is the point 2, 2, 4. This is the point 5, 10. These green points, this is the point 9, 12. And this last one is 12, 18. So you might do this with me, but I'm going to take those 4 green points right there. And this is what regression is, where instead of you doing it by hand, which is cool that you can do it by hand, if I stick those 4 points into my graphing calculator and just tell it to find the equation for me, it's going to find the equation of that red line. It's going to be really close. It's going to be close to this. It's going to be close to this one that we just got, but it'll actually be a little better. So I'm going to do regression with those. You can do this with me if you want, or you can just watch. I don't care. So I'm going to stat, putting these numbers in there. 2, 5. 4, 10, 12, 18. Say again? I'll show you. So I'm taking those 4 ordered pairs. There's going to be a glare on this. So I put in the point 2, 4, double checking my work, 5, 10, 9, 12, and 12, 18. So my X's are list 1 and my Y's are list 2. So the best way to find that red line is to do regression, which is, okay, I entered all those in. Now I say stat, go over to calculate, go down to linear regression. This is what you did on your test. And then I ask it for the equation. Notice it says that this is 97% accurate. Over when we look over here, we see that our red line, those green points are kind of line-ish. They're basically lined up, but they're not perfect. That's why that's not 99% accurate. So notice what I got for my equation. I got 1.276 for the A, the slope here, and then my B, I got 2.07, I guess. So let's do just so this is kind of clear in the notes. 2, 4, 5, 10, 9, 12. This gave the equation y equals 1.276x plus 2.07. The question is, can you see how similar these two answers are? I mean, the second one's actually better. It was less work and it considered all 4 points and it made them go through them perfectly. Notice 5 over 4, if I divide 5 by 4, I get 1.25. Notice how close that is to the slope we actually got. Here I got 2.25, whereas regression got 2.07. This is actually the best. It's the most accurate and it was easier. But it's just kind of cool to be able to do it by hand, at least to understand that, it isn't just magic. It isn't just pushing buttons. It's kind of neat to see what your calculator is doing on the inside a little bit. I'm getting a very similar answer to this. So that's what kind of should happen on your hand in homework. You should get a fairly close answer. Fairly similar. Say that again really loud.
Right, do you prefer which way you write the slope in a fraction or decimal?
No, good question. Do I care what way you write the slope, fraction or decimal? No, don't care. I want you to feel kind of good about either one of them. So let me pull up. So ask me any particular questions you want about this, but notice this one's a little more complicated. But it's useful. It's interesting. Again, I've used this example a lot just because I wanted to make sense, because here we're trying to establish a relationship between the length and the weight of a beam. This is very similar to what you just did in the sense that there's 4 points that aren't very accurate, but there's a line that goes through them. Notice across the bottom, no problem, because each box is worth 1, 10, 11, 12, 13, 14, 15. But as Shelley was pointing out, when you go up the side, it's not quite that simple. So to get from 200 to 400, let's see, there's 1, 2, 3, 4, 5 boxes there. So that must be 40. So 240, 280, 320, 360, 400. Yeah, each box is worth 40. So it's not as easy to count the slope here, which is probably why it's probably easier to go y minus y over x minus x. So I said loop closely and find 2 points that the trend line passes through and use them to find a linear model or a linear equation. That's what we just did a second ago. So, you circle them yourself. There's a really good one right there. I kind of purposely tried to make this hit lots of them just to make it easy for you. There's one way up there. By the way, it'll actually be a little better if you choose one way up here someplace and then one way down here. They'll be a little more accurate than if you choose 2 that are kind of really right next to each other here. But that one looks awesome right there, 45 and whatever that is over there. So you should be able to find the equation yourself by hand. And then if I skip down to number 3, use regression in your calculator with these 4 ordered pairs. Notice I listed them up here so you don't have to count them yourself. I listed them up here. But then also it's kind of cool to be able to do this by hand, actually do regression by hand. We said that according to your note sheet from the last section, you can find R, the correlation coefficient, using a complicated formula. You should be stealing, as I said here, X bar, Y bar, S of X and S of Y from your TI-84, steal those from them. And then we had a method to find the R value and Y hat. Remember, the Y hat is the regression equation. So cheating on your calculator doing regression is way easier, but you can actually use these ingredients and come up with that regression equation by hand. Basically, your answer for 2 and 3 should be exactly the same. It's just 2 will be a pain in the butt because you're doing it yourself kind of by hand, whereas 3, no problem. Just let your calculator do the whole thing. So I would like to shut up and let you ask me one-on-one questions about that. And if I remember right, this isn't due for a couple more days. Is it 3rd? I forgot. Yeah, it's not due till February 3rd, a couple of days, but I'll give you a chance to ask any questions about that you want to. But you should get 100 on this. Like, stay after, ask me questions until you get it. Okay, rest of the time's yours to do with what you will.
I used it this multiple times and I still have what I got here. I double check all my calculations, but I think I'm missing a step or something.
Excuse me. I'm gonna stick.
You're gonna do it on the spot.